Hello everyone, my name is Srikar Vaddela. This summer, I worked as an NSF RU student here at UT Dallas. My project asked a simple but important question. Can large language models help us find bugs in code? And does how we prompt them actually matter? Specifically, I evaluate a structured chain of prompt framework for fault localization in Python. And I test it in two ways, on real bugs and on artificial bugs created using mutation testing. Let me walk you through what I did and what I found. Let's start with why this matters. When software breaks, the single most time consuming part of fixing it usually isn't writing the fix, it's finding the broken function in the first place. That search dominates debugging time. Now, when a test fails, it produces a traceback, a report of where the program was when it crashed. The promise here is if a model can read that traceback and correctly name the faulty function, we save developers a huge amount of effort. But there's a catch. I'll come back to it repeatedly. The model only helps if it's genuinely reasoning about the failure, not just parroting back what's already printed in the traceback. To study this properly, I used 156 real bugs drawn from 12 real Python projects, each with a genuine failing test traceback. Before the method, two definitions. The first is mutation testing. Mutation testing is a technique where you deliberately inject tiny artificial faults into working code, one small change at a time. For example, you flip a plus into a minus, or an equals equals into a not equals. Each of these altered versions is called a mutant. You then run the test suite. If a test fails on the mutant, we say the suite killed it. The more mutants a suite kills, the better it is at catching bugs. So mutation testing is the standard way to measure how good a test suite is. For my purposes, mutants have one huge advantage. Because I created the fault myself, I know exactly which line is wrong. That gives me the perfect ground truth, an essentially unlimited supply of bugs, a clean control complement to the messy real bugs. The second definition is a method I'm actually testing, chain of prompt. The naive way to use an LLM is a single prompt. You hand it the error and ask in one shot, like which function is broken. Chain of prompt instead breaks that into a short sequence of steps, where each prompt builds onto the previous answer. In my case, three steps. Understand the error what actually means. Second, narrow down to the suspect region of the code. And third, name the specific function. So single prompt is one call and one answer, which is fast, but shallow. Chain of prompt is three calls that refines the answer step by step. The hypothesis behind it is that this extra structure forces the model to actually reason about the failure, rather than pattern matching the traceback. Whether that hypothesis holds is basically the whole talk. That leads us to three research questions. First, on prompting, does chain of prompt localize more accurately than a single prompt? And just as important, for which kind of bugs? Second, how does accuracy vary with things like the type of failure and the difficulty of the bug? And third, on training bias, does a model perform better on real bugs, which may have actually appeared in its training data, than on synthetic mutants, which definitely have not? If real bugs scored much higher, that could mean the model is partly remembering rather than reasoning. I'll answer all these three in the coming slides. My data comes from two sources. The first is Bugs in Py, a benchmark of real defects from 17 well-known Python projects, things like Scrappy, Luigi, Ansible, and Pandas. For each bug, it gives me the buggy version of the code, the developer's actual fix, and the specific test that exposes the bug. The second source is mutants, generated with six standard mutation operators. Having both is deliberate. Real bugs are realistic, but messy, while mutants are artificial, but perfectly labeled. Using both lets me separate the effect of the prompting strategy from the effect of how realistic the fault is. Here's the full pipeline, end to end. Step 1, reproduce. I check out the buggy version of the code and run the failing test to capture a real traceback. Step 2, ground truth. I take the developer's fix and map the change lines to the specific function they belong to, using the code's abstract syntax tree, its structural parse. Step 3, build the evidence. I bundle together the error message, the stack trace, and the buggy code snippet. That's what the model actually sees. Step 4, the two strategies. I run both the single prompt and the chain of prompt on the same evidence. And step 5, score. I check whether the model named any function the developer actually changed, using a whole word match so that I don't get fooled by partial name coincidences. That pipeline runs identically for both strategies and for both fault sources. which is what makes the comparison fair. Now, I'll slide over rigor, because before I can trust any accuracy number, I have to trust the grader. My very first version of the ground truth extractor read the faulty function from the visible context lines shown in the diff. That sounds reasonable, but it breaks into a specific way. When the change line sits deep inside a long method, the function's definition line is too far up to appear in the diff window. So what the extractor does is it couldn't tell which function it belonged to. So it silently recorded a blank or wrong answer. The consequence was very severe. 20 of my 44 bugs at the time were unscorable by construction. The model literally could not be graded correctly, no matter what it answered. I rebuilt the extraction to parse the actual buggy source file with the AST, which always knows the enclosing function. That cut the unscorable set from 20 down to 2. I'm dwelling on this because every single number in the rest of the stock depends on this fix being correct. Here's a concrete look at what these operators do. Each one rewrites just a single token. A plus becomes a minus, a true becomes a false, and so on. Because it's one token change, the faulty line is known exactly by construction. That's what makes mutants such a clean oracle. But it's also the catch. A one token single line fault is far easier to localize than a real bug, where the fault is semantic and can span several lines. That difficulty gap is exactly why my training bias question is hard to answer cleanly, and I'll be upfront about that limitation later. Here's the scale of the whole study: 156 real bugs, each with a genuine reproduced traceback, across 12 projects, 149 mutants, where 125 from lighter, easy to go modules, and 24 from heavier ones like pandas, matplotlib that need special environments. And critically, every one of the 17 bugs in Py projects is represented by at least a few bugs or mutants. So I have full coverage of the benchmark. No project was left out. Now to results. Starting with a baseline. Before spending anything on a large model, I ran the whole pipeline with a small, local 1 billion parameter model, Llama 3.2. It scores about 27% with single prompt and 25% with chain of prompt. So chain of prompt is actually slightly worse here. But the point of the slide isn't that chain is bad. It's that a model this small is simply too weak to take advantage of a better prompt. There's no reasoning ability for the extra structure to unlock. What this baseline does prove is that my pipeline runs end to end and produces sensible measurements. To actually answer the research question, I used a capable model with the results on the next slide. So here's that capable model, GPT-5. On the real bugs, averaged over 3 runs on 144 bugs, and the picture changes completely. Accuracy roughly triples compared to the 1 billion baseline. Single prompt reaches 81.5% and chain of prompt reaches 83.6%, with a very low variation between the runs. So chain of prompt leads by about 2 points. Now 2 points is a real edge, but it's modest. And if I stopped here, you would reasonably say that's marginal. The interesting part of my project is understanding why the headline number is misleadingly small, and that's what the next several slides unpack. To explain, let me walk through one real bug in detail, bug 22 from Scrappy. The program crashes on line 159 inside a function called xt characters when it calls .decode on a value that turns out to be a boolean, and booleans do not have a decode method, hence the error. Now if you take a look at the traceback, it points you right at line 159. But here's the thing, that function is actually innocent. It only ever receives a value that someone else handled. The real defect is up on line 148 in the column export XML field, which passes a non-string value straight through without converting first. And sure enough, the developers fix edits line 148 and not 159. So this is a bug where the traceback points at one place, but the actual file lives somewhere else. Keep that gap in mind because it's the heart of my main finding. Now, watch what each strategy did on that exact bug. Same evidence, same model, but two different conclusions. Single prompt answered XT characters, the function named on the traceback. In other words, it just read the answer of the deepest frame of the trace. Chain of prompt answered export XML field, the caller, one level up, which is where the fix actually belongs. Why the difference? Single prompt did exactly what a naive metric rewards. It echoed the trace. But chain of prompt was forced to explain the failure before naming a function. And that reasoning step is what moved it off the traceback and onto the real defect. And this wasn't a fluke. Chain of Prompt got this bug right in all the three runs. This is precisely the kind of bug my next slide isolates. This is the most important slide in the talk, so let me slow down a bit. I discovered that 55% of my bugs, which is 86 out of 156, the traceback already names the faulty function. Think about what that means. For more than half the bugs, the answer is sitting right there in the evidence. Localizing them isn't a reasoning task at all. It's a copy task. And you can see it on the left bars, on that leak subset. Both strategies score around 90%, and chain of prompt is even a shade worse, because when the answer is handed to you, extra reasoning steps can only introduce noise. But now look at the right bars, the no leak subset, the 70 bugs where the traceback does not give away the function. Here, a model has to genuinely reason, like the scrappy example. And on the honest subset, the picture inverts. Chain of prompt beats single by 4.8 points, more than double the headline gap. So the real story is this. My raw 2-point average is diluted by 86 copy task bugs that were never a real test of localization in the first place. Once you separate them out, chain of prompt's true benefit becomes clear. Leakage isn't the only thing that matters. The size of the code file matters too. I split the bugs into three bands by the module size. On small modules under 10 kilobytes, both strategies are near the ceiling around 90%. There's simply nothing left to win. In the middle band, which is 10 to 40 kilobytes, is the sweet spot. Chain gains almost 7 points over single. But on the largest module, over 40 kilobytes, the effect reverses. Chain actually does worse. The intuition is that a longer reasoning chain has more room to take a wrong turn early and then compound that mistake before it converges. So chain helps in a specific middle zone of difficulty. And notice, the earlier 1 billion model collapsed on large modules. GPT-5 holds up far better, which is a capability story in itself. If I zoom all the way out, everything I've shown collapses in one clean pattern, a difficulty gradient. Here are four tiers, from easiest to hardest: heavy mutants, light mutants, real bugs, and the hardest real bugs. What's the gap between the two bars as you move right? At the easy end, both strategies are pinned at the ceiling. No difference. In the middle, chain pulls ahead. And at the hard end, the bars actually cross. Chain falls about 5.5 points behind. So, the benefit of structured prompting isn't constant. It appears only a narrow band. The task has to be hard enough that reasoning helps, but not so hard that the model gets lost. Once the model is out of its depth, the structure stops helping and starts hurting itself. Breaking it down in another way, but a type of error. Chain helps most on attribute errors, where it gains almost 10 points. That actually makes sense. An attribute error is about something that should exist and doesn't. So reasoning about what the code intended generally pays off. And assertion errors, which are just wrong computed value and are the most common type, chain barely moves the needle because a wrong number gives the model very little to reason from. And simple lookup errors like key error and index error are already solved by both strategies. So chain of prompts advantage is concentrated on the failure types, where understanding intent matters the most. And here's the same conditional pattern, project by project. This chart shows the change in accuracy going from single to chain. Chain is clearly not uniformly better, but it's conditionally better. It wins solidly on Scrappy, plus 7.6 points, and on the other mid-sized targets where narrowing the search really pays. But it loses badly on projects like TQDM and PySnooper, where again, an early wrong turn in the chain compounds instead of self-correcting. I want to be honest that these per project numbers are on a small samples, so I treat them as exploratory. But the direction is consistent with everything else. Now let me answer the training bias question. The worry was, since real bugs might be in the model's training data, maybe it scores higher on them by remembering rather than reasoning. If that were true, real bugs should outscore mutants, but they don't. It's the exact opposite. On a fair leakage control comparison, real bugs sit at 66%, while mutants on the same project score nearly 90%. Mutants score much higher, which is the exact opposite of what a memorization effect would predict. So I find no evidence of training data bias. I'll be upfront though. Mutants are also simpler by construction, so this comparison mixes memorization with difficulty and can't fully isolate the two. It's an honest negative result, not a clean proof. This is maybe my cleanest single result. I take the same 44 bugs and run them on both models. At 1 billion parameters, chain of prompt is worse than a single prompt. The model can't exploit the extra structure, and the reasoning steps just compound its own errors. But at GPT-5 scale, the ordering flips. Chain wins by 4.7 points. So the effect literally changes sign as the model gets more capable. The lesson is that chain of prompt is not a free improvement. You can bolt onto any model. It's capability gated. It only pays off once the model is strong enough to actually use a structure. On a weak model, it backfires. Let me be candid about the limitations. On measurement, I found and corrected five distinct classes of artifact that would have silently corrupted my numbers, including tests that reflect a module's own source, timeouts being miscounted as detections, and the ground truth bug I showed earlier. On statistics, several of my results sit near the 0.05 significance line across many different splits. The two most important ones, leakage and module size, were planned in advance, which makes them credible. But the per project and per failure type breakdowns are exploratory and probably wouldn't survive a strict multiple comparison correction. So I present them as suggestive. And on design, as I said, mutants can fully separate memorization from a difficulty. So my third question stands as an honest negative result rather than definitive test. So to bring it all together, my headline finding is that chain of prompt improves false localization by about 5 points on the honest no leak subset, and that this effect was completely hidden in the raw average, because more than half the bugs leak the answer in their own traceback. But the benefit isn't universal, it's conditional. It shows up on mid difficulty bugs and mid-sized modules. It vanishes when the task is trivial and the model's already at the ceiling, and actually reverses on the very hardest bugs. On top of that, it requires a capable model. At 1 billion parameters, the very same strategy hurts. So the real takeaway of my summer is this. Better prompting is not free capability. It's a lever, and it only works within a specific band of difficulty, on a model strong enough to pull it. Understanding where that band is exactly what this project mapped out. Well, that's my work for the summer. Thank you to the NSF, to UTD, to my advisor Professor Eric Wong, and my mentor Kevin for their guidance.